Hi there, this is Shoot Socrates. Welcome to today's video on infinite series where we are going to talk about the ordinary comparison test. And you might say, ordinary? Why so ordinary? Well, the next video is going to be about the limit comparison test. So that is a different kind of comparison test, and we're going to see it after this video. So without further ado, we're going to go to section 2E of our textbook. And again, if you don't have a copy of my textbook, just go to the description of the video and you will find a link there to Dropbox where you can download my textbook. All right, let's go check it out. Here we go, section 2E. We are going to decide whether an infinite series is going to converge or diverge by comparing it to a second infinite series. Now, that second series is going to be a much simpler series than usually what we are given. And by simple series, well, we have encountered so far convergent and divergent geometric series, as well as convergent or divergent p-series. So remember that a geometric series looks like summation r to the n, where n can start at 0. And we know that these series converge when r is less than 1, but positive in absolute value, and they diverge when r is bigger than 1 or less than or equal to -1. Similarly, we saw in the video about the integral test that the p-series, summation 1 over n to the p, converges if p is bigger than 1, but they diverge when p is between 0 and 1. So if this is new to you, I suggest that you check out those two previous videos. All right, so we are usually going to take advantage of one of those kinds of infinite series in order to apply the ordinary comparison test. And here it is. So what does the OCT say? Suppose we have a sequence a sub n, n from k to infinity, and the sequence is made of non-negative terms. In other words, they're always positive or 0. Then, part A, if we can find another sequence, let's call them b sub n, and a sub n is less than or equal to b sub n for all n which is at least k, and this series made of bigger terms converges, then our series also converges. The series made of the terms a sub n. So similarly, if we can find another non-negative sequence c sub n, where a sub n is at least c sub n for all n at least k, and this smaller sequence, when you form the infinite series made of this smaller sequence, diverges to infinity, then our original series, the one made with a sub n's, also diverges to infinity. So one easy way by which you can remember this theorem is that if a bigger series converges, then the smaller series converges. And conversely, if the smaller series diverges to infinity, then the bigger series must also diverge to infinity. But also, make sure you remember that the terms in the sequence that makes up the series must consist of non-negative numbers. All right? It cannot work if you have sometimes negative, sometimes positive terms in your series. All right, so in our last video, when we talked about the integral test, I gave you an example first, and then I showed you with a proof that the integral test is true in general. We're going to do the opposite today, mostly because the proof of the OCT, the ordinary comparison test, is relatively short and simpler than the integral test. Okay? Again, we are going to make use of the monotone convergence theorem, which we saw in the integral test as part of its proof. We are going to take the partial sums of our sequence, and of course, since the terms are non-negative, the partial sums can only get bigger because you're either adding 0 or a positive number. All right, so the sequence of partial sums is monotonic increasing, and we know that the series converges if and only if the sequence of partial sums converge. By the monotone convergence theorem, the sequence is going to converge if and only if it is bounded, and in this case, more importantly, bounded above. The sequence is increasing, and so we need an upper bound for the sequence in order for it to converge. Okay, so let's think about part A. What if there is another sequence which is bigger, each term in the new sequence is bigger than the corresponding term in our original sequence? All right, so let us look at the partial sums. We have a partial sum for the A's. We can also write partial sums for the B's, but this time let's use the symbol capital T sub n instead of S sub n, because that is for the partial sums of the A sub n's. Okay, so we have T sub n is bk plus bk plus 1 all the way up to bn. All right, we are given that this infinite series converges, made of the B sub n's, so the partial sums for summation of B sub n must converge to some limit, and let's call that limit t. Okay, but we know that each A is less than or equal to each B, so therefore the partial sums for the A's must be smaller than or equal to the partial sum for the B's. But again, the T sub n's, the partial sum for the B's, is made of positive terms. So it is also an increasing sequence of positive numbers. And so the limit of the T sub n must be bigger than the terms of that sequence. T sub n is less than or equal to the limit t. And so t is also an upper bound for the sequence of partial sums S sub n for our A sub n's. Okay, so that means that our series summation n equals k to infinity of A sub n must also converge. Its partial sums are monotonic increasing and bounded above. All right, so let's now take a look at part B. What if we have another series C sub n, another sequence C sub n, and the corresponding infinite series diverges to positive infinity? So this time, let's write the partial sums as U sub n, which is ck plus 1, all the way up to C sub n. All right, so since each of our A sub n's is at least equal to or bigger than the corresponding C sub n's, then the subtotals, the partial sums for the S sub n's, must be at least the partial sum U sub n. Okay, but summation Cn diverges to infinity, so these partial sums diverge to infinity. The limit of U sub n must be positive infinity. So if that is tending to positive infinity, then S sub n should also tend to positive infinity. In other words, our series must also diverge to infinity. All right, let's go to our workroom and look at some examples. All right, so I thought it would be fun if we reviewed two of the examples that we saw in our last video. Ooh, 3 actually. So our first example was summation 1 over n to the 7/5. 7/5 is bigger than 1. So this is a convergent p-series. We changed 7/5 to 5 over 7, flipped the exponent. And we saw that by the integral test also, this series diverges to positive infinity. Now, if the exponent of n is simply 1, we have summation of 1 over n, which, by the way, is called the harmonic series. I may not have mentioned that explicitly in the video, but I mentioned it in the textbook. The harmonic series diverges to infinity. And of course, in general, if you have a p-series summation 1 over n to the p, that diverges to infinity if p is between 0 and 1, including 1, as we saw over here. And it converges if the exponent p is bigger than 1. Now, we might also need the geometric series. And we know that these geometric series converge if and only if the common ratio r is less than 1 in absolute value. So we mentioned that in the first part of our video. Okay, so let us consider as our first example this infinite series. Summation cosine 1 over n to the 7/5. Okay, so we have n to the 7/5 from our previous example. Okay, do we want to integrate this? I don't think so. I can't even think of a way to do that, even by integration by parts. Ooh, yuck. Okay, but let's think about cosine 1 over n. We have to start at 1 because we don't want to divide by 0. So what is cosine 1 over 1? That's in radians, of course. 1 radian, cosine of 1 radian, is about 0.54. What is cosine 1/2? It is approximately 0.8. Oh, it got bigger. Yes, of course, because the angle is getting smaller. 1/2 is over, 1 is here, 1/2 is over here. So the cosine, the x-coordinate, is getting bigger. What about 1/3? Cosine of 1/3 is approximately 0.944. Yeah, we're getting closer to 1 because as the angle is getting smaller, the x-coordinate is getting bigger, getting closer to 1. Aha! So of course, it's always positive because we're in the first quadrant, and n to the 7/5 is also positive. So we can apply the ordinary comparison test, but we need a second series, which is either bigger or smaller than the series that we're looking at here. Okay, that's the trouble with the ordinary comparison test. You're only given one series. You're not told, oh, by the way, compare it to this. Okay, we're not going to tell you what you should compare it to. You need to figure that out for yourself. Okay, but now that we understand the numerator seems to be increasing, but cosine is never bigger than 1. Okay, so we can certainly say that cosine 1 over n is, well, it's going to be positive, and because we're not going to start with pi over 2. There's no pi over 2 in the conversation. So the cosine is less than or equal to 1. Okay, and so if we divide all the parts of this inequality by n to the 7/5, which is positive, then we will maintain this compound inequality, right? So 0 over n to the 7/5, which is of course just 0, it's kind of silly, is less than cosine 1 over n to the 7/5, and less than 1 over n to the 7/5. Okay? So of course the left term simply says that 0 less than the terms of our series less than 1 over 7 n to the 7/5. Okay? But we saw above that summation n equals 1 to infinity of just 1 over n to the 7/5 is convergent. And so by part A of the ordinary comparison test, our series, which is summation cosine 1 over n to the 7/5, is also convergent. Okay, excellent. So shall we dare flip the exponents? Okay, so follow up. What if we had cosine 1 over n to the power 5 over 7? Okay, let's flip the exponent just like we did in the integral test. Okay, so consider this new series. Okay, again, everything is positive, of course. We just changed the exponent. So it's still true that if we divide all the terms in the compound inequality, where is that? This one. If we divide all of this by n to the 5 over 7, that's still going to be true. Okay? So we can start that way. That is a true compound inequality. And it remains true if we divide everything by n to the 5 over 7. Okay, so 0 over n to the 5 over 7 is less than cosine 1 over n divided by n to the 5 over 7 is less than 1 over n to the 5 over 7. Okay. However, this bigger series is no longer convergent, right? Let's review. This new series diverges to infinity. But the ordinary comparison test says, if you're in part A, and that's where we are because our series is smaller than something else, then that bigger series must converge. Okay, so we're not in part A. Wait a minute, let's go back to our PDF. Maybe we're actually in part B. Let's check. All right, are we in part B? If we can find another sequence, also non-negative, which is this time smaller, no, the 1 over n to the 5 over 7 is bigger. Okay, so we are neither in part A nor in part B. We're in limbo. Okay, so that inequality does not help us. We're neither in part A nor in part B, so we have to think of something else. All right, so unfortunately, the bigger series, which is summation of 1 over n to the 5/7, is divergent. So we are not in part A. We checked, we just did it. And we are not in part B either. So we are not correctly using LC. Okay, you have to make it work. If you are going to compare your series to a bigger series, that bigger series had better be convergent. If you want to compare it to a smaller series, that smaller series had better be divergent. Okay, so we have this series. We know it's divergent, but we know it's not bigger. Okay, so let's look at our data. We said that cosine 1 is 0.54, cosine 1/2 is 0.877, cosine 1/3 is 0.944. And of course, as n increases, 1 over n decreases. And so cosine 1 over n increases, okay, because cosine is a monotonic decreasing function between 0 and pi over 2. Okay, so it means that 0.54 is the biggest value that we are going to get for it's the smallest value that we are going to get for cosine 1 over n. Okay, so in other words, the cosine 1 over n factor are at least 0.54. Let's just round it down to 0.5, which is 1/2. Okay, so instead, we observe that the smallest value that we get for cosine 1 over n, okay, where are you? There you are. For cosine 1 over n is 1/2. And so we get the true inequality. Cosine 1 over n, I'm going to steal that whole thing, is not less than or equal to, but greater than or equal to. Not 1, but 1/2. 1/2 over n to the 5/7. And of course, we know that this series is divergent. Does it matter if the numerator is 1/2? No, it doesn't. It's just a real number which we can factor out of the summation because it's a constant. All right, since that series is divergent, the series summation of 1/2 over n to the 5/7 is also divergent. All right, so now we are correctly applying the ordinary comparison test. We have come up with a smaller series which is divergent. So we are now correctly in part B of the OCT. By part B of the OCT, since the smaller series is divergent, our series is also divergent. Ta-da! All right, so you have to do essentially two things. One of two things. You should either pick a bigger series which converges, or you have to pick a smaller series which diverges. And there's the rub. That's the hard part. We don't know whether we should open door A or open door B. The series is hiding behind one of those doors. Okay? We don't really know. So what do you have to do? You got to try. Okay? And of course, do your homework, because in the homework, you will see series similar to these ones. And you need to remember, okay, I think this one converges. We compared to this thing and it was bigger. And so blah, 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 blah. All right. So what we're going to do next is we're going to introduce a new character to our infinite series. A character that you have seen before. Here it is. I believe this is the first series that we are going to look at where the natural logarithm is involved, ln of n. So consider the infinite series summation n equals 2 to infinity ln of n over n to the 5/7. Okay, so we're starting at 2. We can't start at 0, definitely. ln of 1 is 0, so it's kind of stupid that we would plug in 1 just to get 0. So let's start at 2. Okay, so of course we know that ln of x is an increasing function. Okay, increasing, concave down. So yeah, ln of 2 is approximately 0.69. Okay, not a very big number. But if we increase our n, let's say ln of 8, then we're going to get a bigger number. What if it were ln of 800? Then we're going to get an enormous number, which is not enormous at all. Remember, ln grows very, very slowly. So if we put 3 more zeros, 1, 2, 3. How much are you? Yeah. Oh, please, that's not even $20. Okay. ln of 800,000 is not even 14. Okay. It's an increasing function, but it's not increasing very quickly. Okay. Now, we said that the smallest value of cosine 1 over n is about 0.54. So it's definitely bigger than 1/2. Okay. But yeah, it looks like these numbers are getting big. So definitely ln of n is going to be bigger than 1. Okay, and if you say, can't we make it 2? Okay, fine, 2. But you have to start at n equals 7. So no, let's keep it 1. Okay, ln of n is bigger than 1 if n is at least, yeah, let's check. When will we break ln to be 1? Well, ln of e is 1. So I think if you are at least 3, then you will be 1 something. What is ln of 3? There you go, 1 something. All right, so that is true if n is bigger than 2, at least 3. Okay, all right, so are we again in part B of the ordinary comparison test? Yeah, we have a smaller sequence And the infinite series made of that sequence, we know that is divergent. So we have exactly the same conclusion that we get from our previous example. So I can just cut and paste this, and I'll edit it accordingly. Since the smaller series is divergent, we don't even have to use the 1/2. The series summation ln of n over n to the 5/7 is also divergent according to part B, of the OCT. And we can put a period on that sentence. All right? So we have a smaller series which diverges. So the bigger series that we have is also divergent. Okay, so we started with 1 over n to the 7/5. We had cosine 1 over n to the 7/5. So don't you think it's only fair that we have yet another follow-up, but this time, instead of n to the 5/7, we go back to n to the power 7/5 in the denominator. Okay, so once again, you have to be in either part A or part B of the OCT. We can start with thinking about ln of n, like we did over there. Ln of n is bigger than 1. So ln of n over n to the 7/5 is again bigger than 1 over n to the 7/5. We can again say that ln of n over n to the 7/5 is greater than or equal to 1 over n to the 7/5. But this smaller series is convergent. Okay, it's not summation 1 over n to the 5/7. It's 1 over n to the 7/5. 7/5 bigger than 1. So that smaller p series is convergent. Okay, thus we are not in part B, nor are we in part A of the OCT. Okay, so once again, we are not using the OCT correctly. It's not fitting. We have a smaller series, but it's a convergent series. All right, if you choose a smaller series, the smaller series has to be divergent. Okay, so we need something a little bit stronger, something that has to do, of course, with ln of x. All right, and this is the very, very strong property. It's an inequality that we are going to take advantage of in order to finish off our problem. The graph of the natural logarithm function, y equals ln of x, is eventually below the graph of any power function, x to the power k, where k is positive. This means that ln of n is less than n to the k for any positive number k if n is big enough. Okay, so make sure that the power of n is positive, because if it's negative, then that's definitely not true, because then if you have a negative power, it will be 1 over n to the something, which is a positive power, and that goes to 0. All right, so ln of n does not go to 0. Otherwise, ln of n would be smaller than something that goes to 0. By squeeze, ln of n will also go to 0. We know that's not true. Okay, the proof of this property is very simple. It's basically just L'Hopital's rule. Let's take a look at the fraction that we get when we divide ln of x by x to the k. As x goes to infinity, ln of x goes to infinity, x to the k also goes to infinity. So by L'Hopital's rule, which we can apply, it's infinity over infinity, we take the derivative of ln of x, which is 1 over x, divided by the derivative of x to the k, power rule x to the, k times x to the k minus 1, that 1 over x, that x can go down to the denominator, canceling with that minus 1. So you get 1 over k x to the k, and of course, as k goes to infinity, that limit is equal to 0. Okay, so if a fraction is getting closer and closer to 0, well, 1 is up here, 0 is down here. So eventually, that fraction has to be smaller than 1, because it's going to get closer and closer to 0. Well, if that fraction is smaller than 1, then the numerator has to be smaller than the denominator, which is what this thing is saying. Okay? If you don't believe me, maybe you will believe GeoGebra. All right, so let's go over there and play for a little bit. All right, here we are. So let's take a look at f of x, which is ln of x divided by x to the power 7 over 5. Ooh, okay. So there it is. Yeah, we can already see that it's smaller than 1 right away. And as we move to the right, yep, it's getting closer and closer to 0. Okay, so you don't have to wait very long. ln of n is going to be smaller than x to the 7/5. Okay. However, that doesn't exactly help us directly. So here's what I'm going to do. I'm going to make that exponent even smaller. Okay, 7/5, that's kind of big. That's bigger than 1. What if it's 3/5? Okay, that's now smaller than 1. Ooh, okay, so it's fighting a little bit, right? It went up a little bit higher. So let's make this even smaller. What if it's only 1/5? Ooh, oh, okay, now I'm worried, because that's 1, it's now bigger than 1. Okay, yeah, that's 1, it's still bigger than 1. Uh-oh, oh no, oh no, it seems to be staying above 1. Okay, the exponent there is really small, still positive, 1/5 is still positive, but it's really small. So let's see how long we have to wait. Let's plug in 1,000. Ooh, still bigger than 1. 10,000? Ooh, bigger. 100,000? 1,000,000? Ah, okay, there you go. No wonder we're not getting anywhere close to 1. We have to wait until x is maybe 1,000,000, maybe less than that, so that we'll get a number which is smaller than 1. Okay? So, yeah, you can make this even smaller. And then you have to wait a little bit longer. But the point here is that if you wait long enough, ln of x will be smaller than x to the 1/5. Okay, so yeah, let's use that to solve our problem. All right, however, we just saw in GeoGebra that if you wait long enough, and we saw that x at least 1,000,000, that ln of x is going to be smaller than x to the 1/5. Okay, x to the 7/5, no problem. 3/5, little bit of an issue. 1/5, big issue. But still, if you plug in a big enough number, you will get something smaller than 1. Okay, and so thus, by dividing both sides of this inequality by n to the 7/5, which is in our denominator, we now get, take this and divide this by, turn it to a fraction. Where's my fraction? There you are. Divide by n to the 7/5. That will be less than, whoops, so that will be, I will turn that into an n, and I will turn that into n also. So yeah, let's do that here, where n is at least a million. Okay, now everything's in it. It'll be less than n to the 1/5 over n to the 7/5. Okay, but by the rules of exponents, what are we going to get? Well, 7/5 is bigger than 1/5. So we can bring the 1/5 down to the denominator. 7/5 minus 1/5 is going to be 6/5. 6/5 is bigger than 1. And so the infinite series made of those terms will be a p-series. P is 6/5, bigger than 1. So it's going to be a convergent p-series. Aha. And since 6/5, 6 over 5 is bigger than 1, the p-series summation, where's my summation sign? Okay, let's steal it over here. And we can start at 2. 1 over n to the 6/5 also converges. Okay, so thus we found a bigger series which converges, and so by part A of the OCT, our series, which was the original one, this one. Also converges. All right, so by using this inequality, ln of n less than n to the 1/5, not 7/5, but only 1/5, we were able to cut down 7/5 by 1/5 and get an exponent which is still bigger than 1. Okay? So, of course, we found that 1/5 by essentially, not going to lie to you, we were playing in GeoGebra. Okay? 7/5, oh, no problem, you're already smaller than 1. 3/5, still smaller than 1, but 1/5, oh, now it was starting way above 1. You're not going to get GeoGebra on your test. Okay? So, how are we going to decide then? Is the 1/5 going to be good enough? Okay, what would be a good way, a good scientific way by which we can pick the k? Okay, so we know that in general, ln of n will be smaller than n to the power k. So depending on the problem, how are we going to choose k? All right, so let's start over. Consider, literally start over. Consider our original problem. Okay. If we didn't have GeoGebra, how will we pick the exponent k such that ln of n is smaller than n to the k, and we can use part A of the OCT. Okay, so, well, we know that this inequality is true for any k, any positive k. So again, we can divide both parts by n to the 7/5, and the inequality will still stay true. So let's just steal this. I'm sorry, this one. This is what we should steal, because we don't know what the k is, and it is less than or equal to. Okay, so we know that the numerator will be n to the k. We don't know what the k is. But remember what happened. K should be small enough so that 7/5 is bigger than k, definitely. And the exponent has to stay positive in the denominator. Okay? So this is going to turn into 1 over n to the 7/5 minus k. All right. So now, for the series, summation, and I'm going to borrow this, summation 1 over n to the 7/5 minus k to be a convergent p-series, we must have that the exponent 7/5 minus k has to be bigger than 1. Which translates to, okay, so let's bring the 1 over and switch it with the k, the minus k. So we'll get 7/5 minus 1 greater than k. Or in other words, 7/5 minus 1 is 2/5. 2/5 greater than k. All right, so we have to pick k so that k is smaller than 2/5. All right, we picked 1/5, which is of course smaller than 2/5. Since 1/5 is less than 2/5, our choice of k equals 1/5 works. Past tense. We already saw that it works. Can we pick anything smaller than 2/5? Sure. There are lots of fractions which are smaller than 2/5. If you want a denominator of 5, yeah, you're out of luck, because the only thing smaller is 1 over 5. The only thing smaller than 2 is 1. Can't be 0. It better be positive. Okay, but 2/5 is 0.4. So how about 0.3? Okay. 0.3 is 3 over 10. Since k equals 3 over 10 is also smaller than 2/5, we could also have chosen 3/10 to finish the problem. Let me bring that to the last line. All right, there we go. Okay. So actually, yes, I am at the last line. Oh, wow. Not an hour this time. Not even 45 minutes. Well, just about. All right. So that's our video on the ordinary comparison test. Coming soon to a monitor near you, we are going to talk about the limit comparison test. Okay. So until then, I hope you enjoy the rest of your day. Bye.